Welcome to week 8. This video is on section 9.1. We are going to obtain a point estimate for the population proportion. We've already done this, but we're going to be using it in a different way. Construct and interpret a confidence interval for the population proportion, and determine the sample size necessary for estimating a population proportion within a specialized or specified margin. So this kind of goes hand in hand with 8.2 that we did last week. And so kind of piggybacking off of that a little bit. So let's just jump right in. So point estimate, you may remember this, and I don't know why these things don't show up right, is a value of a statistic that estimates the value of a parameter. So the point estimate, we use that as the mean. So we put X, which is the number of successes or the number of individuals with a specified characteristic, and then we divide it by N, which is your sample size. So our point estimate is the number of successes divided by your sample size. So we're gonna, I think we may have done this one in 8.2 or something similar, so just as a reminder to calculate the point estimate. So in July 2008, Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. We're going to obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So you just take, I don't know why the equal signs don't save up, 1123 divided by 1783, and you get 0.63. So that is our point estimate. This is really important because wherever we're going to be using our point estimate as our proportion for the problems in this section. So make sure when you have these types of population or problems, you are using the point estimate. All right. So a confidence interval is an unknown for an unknown parameter consists of an interval of numbers based on a point estimate. So the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted like this. Don't worry, it's going to look a little bit better while we are, as we get into it. This looks really confusing. Once we're actually using numbers, hopefully it'll make more sense. Basically, a confidence level of confidence is you'd be able to say, I'm 90% confident or I'm 95% confident. And we're going to, our confidence interval, so the numbers that our interval of numbers will be dependent on how confident we are. So for the numbers probably will be further apart. If we are less confident, they'll be closer together. If we're more confident, because we're going to say that we're confident that most of our data is going to be between two values. So let's just do some math on this and hopefully it'll make sense as we get going. So a 95% level of confidence, that's alpha equals 0.05, implies that if 100 different confidence intervals are constructed, each based on a different sample from the same population, we'll expect 95% of the intervals to contain the parameter, 5 to not include the parameter. So basically, if I take, let's just pick a sample size. So sample size 100, I take a sample here and a sample there, and so we are finding the proportion of individuals that have that success in each of these different samples, and we took 100 different samples. We're going to expect 95% of those to contain our parameter, contain whatever that parameter is that we're looking for. So let's do an example, and hopefully this will help. Oh, I forgot this part. Sorry. Our confidence interval is going to be our point estimate, which remember our point estimate is the mean. That's what we use for our mean, plus or minus a margin of error. The margin of error is a measure of how accurate the point estimate is. So you've heard this, like presidential polls. Let's talk about those because that's something that's really relevant for right now. So you notice when they say that that they think this candidate has 41% of the vote and this candidate has 45% of the vote, and then it'll say plus or minus 5%. That's your margin of error. So based on the confidence level we're looking at and the number of people we polled, we have to come up with that margin of error. So we can tell you it's going to be plus or minus this amount in order to be a certain amount of confident and based on how many people we polled. So this tells us how accurate our point estimate is. So the margin of error depends on 3 factors. Our level of confidence. So as our level of confidence increases, our margin of error is also going to increase. So if I'm 99% confident of something, my margin of error is going to be increase. So if I, 95% confident, I might have a margin of error plus or minus 3%. But then if I go to 99% confident, I might end up with a margin of error plus or minus 5%. So it changes as our level of confidence increases, our margin of error also is going to get bigger. Our sample size. So as the size of the random sample increases, the margin of error is going to decrease. So the more people we poll, the more confident we are that our point estimate is a good indicator of what the entire population feels. So our point estimate, remember, that's based on a sample. So as we sample more and more people, as we question more and more people, our margin of error is going to get smaller. Because remember that law of large numbers? As we poll more and more people, our sample mean is going to get closer and closer to that population mean. So standard deviation of the population, the more spread there is in the population, the wider our interval will be for a given level of confidence. So our interval is going to be bigger if our standard deviation is bigger. But remember from previous lessons, as our n gets bigger, as our sample size gets bigger, our standard deviation is going to get smaller. So it's going to be less spread out the more people we poll. So let's move on. So this is just a reminder, and of course I have some strange things that didn't show up here. So for simple random sample, this is from 8.2. A simple random sample size of n, the sampling distribution of p hat is approximately normal. Remember, our mean is for our mean, we're going to use p hat. Our standard deviation, that shouldn't be an alpha. I don't know why I drew alpha. This should be a sigma. Our sigma sub p hat equals p times 1 minus p divided by n, and we take the square root of that if and only if np times 1 minus p is greater than or equal to 10. Also, remember, each trial must be independent. When we have a finite population, our sample size, has to be smaller than 5% of the population. This is just a reminder. Whenever I have this little guy with the string around his finger, that means it's just a review. All right, next. I don't know why things don't show up. I'm so sorry about this. If you have the PowerPoint in front of you, you should be able to see this, because for some reason things are not showing up properly on my iPad, which is what I use to make these. So here's how we're going to construct our confidence interval for a population proportion. Suppose that a simple random sample size of n is taken from a population. Our confidence interval for p is given by the following quantities. And this is, sorry, these should not be equal. I am so bad with this. Okay, so this is our lower bound is going to be minus. Lower bound is minus, upper bound is plus. So this right here is the margin of error. Remember our p hat, we use that as our mean, and we would subtract that margin of error from our mean, and then we would add that margin of error to our mean. We do this in order to get our confidence interval. So this is p hat times 1 minus p hat divided by n, and you take the square root of that, multiply it by, and I'm going to show you what this is right here. It is z sub alpha divided by 2, this right here is what we call a critical value. This is called a critical value. Let me show you what this looks like on a picture here. Okay. So on our curve, we have our P plus the margin of error and P minus the margin of error. This right here is our mean. And this right here, this big piece right here, this is our confidence interval. We know that of all the sample, that whatever this percent is, of all proportions are going to lie in this region. And these will result in confidence intervals that include the population proportion. So we subtract the margin of error and add that margin of error to our mean, and we know that 95% or 99% or whatever of all sample proportions will lie within this spot right here. Okay, so this is what it looks like. So Z alpha divided by 2 is called the critical value of the distribution. It is the number of standard deviations the sample statistic can be away from the parameter and still result in an interval that includes the parameter. So those standard deviations are going to be, further away from the mean as our confidence interval gets higher, because remember our margin of error gets bigger, so we will include larger standard deviations. But for example, our 90% confidence interval, it can be 1.645 standard deviations away from the mean and still be in that interval that includes the parameter. So let's take a look at this. So this right here is the table that we are going to use for our critical values. So you see over here is our level of confidence. So if I want to say I'm 90% confident of something, I look at this one right here. The area in the tail, that's what our alpha is. Let's go back here. So this right here is our alpha, the area in the tail. So this is the area that is not included in our confidence interval, is the tail. So when we're looking at like the center 90%, or center 90%, 0.5% or 0.05, so 5% is at the top and 5% is at the bottom. So let me draw this here. This is something that a lot of people missed on the test, and so I want to make sure that I point it out. So if I have a confidence interval of 90%, we're looking at the middle 90% of our curve here. This is the area that's going to, and this is the area right here that is going to include our population proportion. So we have 5% up here and 5% down here that is not included in our confidence interval. 5% here and 5% there. That's why we do alpha divided by 2, because the area in each tail is 0.05. So this right here is 0.95 and this is 0.05. If I was looking for a certain value or a z-score, these are the numbers that I'm going to look at right here. And so that's what this is right here. This is a z-score. This is telling me that 1.645 is the z-score. This is the 1.645 is the z-score that corresponds with that 0.95 right there. That's what that z-score is. That's the critical value that I'm going to be using in my calculations, is that z-score. And I'm going to show you how to find this on the z-table in just 1 second. So this is a table that I took out of your book, but if I go to the next page here, I'm going to show you, this is at the bottom of your z-table. So clear all this. At the bottom of your z-table, you have your confidence intervals right here. You have the general amounts. You have the, these are the standard ones. However, your homework is going to occasionally ask for ones that aren't these standard ones. and I'm going to show you how to find those in a couple of minutes. Okay, so that's where you find those critical values based on the levels of confidence that we generally use. All right, so interpretation of a confidence interval. I'm hoping that this will help you a little bit. I know this is a little bit confusing, but let me show you. So a confidence interval indicates that whatever this is, this percent of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. So basically what this is saying is that all of the simple random samples, so if you have a 95%, let's just say 95% confidence, 95% of all of the simple random samples of size n from the population, so let's say that my population is voters, is registered voters, and I took a sample of 100, and I'm looking for a 95% confidence. So I would be, my confidence interval would indicate that 95% of all simple random samples of size 100 from this population of voters, whose parameter is unknown, so we don't know the parameter, will result in an interval that contains the parameter. So I know that that parameter will be in that interval. I know that whatever the actual mean is, whatever the actual value is, will be in that interval. I can be 95% sure that whatever the actual value is will be in that interval. So let's go back to voting. So if I said that a certain candidate has 41% of the votes with a margin of error of plus or minus 3%, I'm 95% confident that I would be 95% confident that the actual number of votes would be between 38% and 44%. 95% confident that the actual number of votes would be between that 38% and 44%. So the 41% is my mean. That is the mean, my p-hat. That is the p-hat. And so I would subtract the 3% from the p-hat and add the 3% to the p-hat. That would be my confidence interval. And I'd be 95% confident that the actual number of percent of votes they have would be within that interval. Hopefully that became a little bit more clear. Let's move on. Let's do an actual example. So in July of 2008, a Quinnipiac University poll asks, we just talked about this, asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. We needed 90% confidence interval from the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. Okay. We already had our p-hat. We already calculated that earlier. So I need to fix these because sadly they don't show up well. So I did the NP times 1 minus P in order to determine if we have a normal distribution. So NP times 1 minus P. So I did all of the math here. I end up with 415.6. That is definitely greater than N. And my sample size, which is 1783, is definitely less than 5% of our population. So thinking of the population of registered voters, it's definitely less than 5%. So I have P minus Z of alpha divided by 2. So this is how we are going to calculate that. Let me write this again because it doesn't like to. So my critical value is, whoa, this is lovely here. My critical value here, I got that from that Z table. The 90% confidence interval, it's on the bottom of that Z table. You just look at 90%. Go over to the Z-score that corresponds with that. It's 1.645. And this here is my p-hat. And this is 1 minus my p-hat. This right here is N. So I do the p-hat minus this confidence in, or this right here, which is my margin of error. Let me just erase all of these extra stuff here. So I have the p hat, which is my mean sub p hat, minus all of this, which is my margin of error. This gives me my lower bound. And then we have the 0.63, which once again is my mean, or my p hat, plus my margin of error, gives me this. So this right here is my confidence interval. That is my confidence interval. So those are my answers. So we are 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is between 0.61 and 0.65. So these two numbers that I have, that's my upper bound and my lower bound. So we can be 90% confident that the actual number of people that are in favor of the death penalty are between these two values. That is our margin of error. So hopefully that made sense. I'm going to show you something real quick on how to find that z-score if it's not one of those normal ones. And then I'm going to set you free to do one of these on your own. So you may need to pause it, or you will need to pause it. You may need to look back on how I did it in the PowerPoint, but let's move on. So let me show you what it looks like in here. So we're going to look at a 95% a 90% confidence interval. So I'm going to look at a 90% confidence interval. I know that is 1.645 because I just used it in a problem and because it was on that little table. But I'm going to show you how I can find it here. So we have, it's a 90% confidence interval, 90% confidence interval. So that right here, so if I take a look at this, my middle 90%, remember there's 5% up here and 5% up there. What I am looking for is this, the z-score of this point right there. I'm looking for that z-score right there. So in order to do that, I need to use 0.95 to find that z-score because I have 5% in the bottom, 5% on the top. So whatever the difference is between this and 100, I divide it in half and then subtract that from 100. So I have 95%. So I'm going to look in the body of my z-table to find 95. Now you can see here, I have this right here and this right here. You notice how 0.9495 and 0.9505, those are equal distance from 0.95. That's why we got the 1.645. I'm not going to ask you to split the difference like that if you're looking them up in the table. I'm going to ask you to take one or the other. But this one, because it was calculated for us, it's right there in the table for us. So let's do another one. Let's take a look at this one. Let's say that we want, just a second here. Let's say that we're looking for an 85% confidence interval. I would like you to pause this right now, and I want you to find the z-score for an 85% confidence interval. That z-score is your critical value. So go ahead and pause, and then come back, and we will do it together. All right, so how'd you do? Okay, so I know that the difference between 85 and 100 is 15. So 0.15 divided by 2 gives me 0.075. This right here. That is 0.15 divided by 2. Now I need to do 1 minus that 0.075. That's going to give me 0.925. This right here is what I'm going to look for in my table. So let's see here. 0.925. And look at that. This right here is really close to 0.925. So my critical value then, the critical value would be 1.44. I bet you would like an easier way to do this. Am I wrong? See, I am not wrong. I know I'm not wrong. So how did we do it before? What did we do before when we were looking for a z-score when we had the percent? What did we do before? We used, so we'll hold on to that because we're going to do an example problem where I actually want you to do the math. And then whoops, there it is right there. I guess I won't do it. Wait, hold on here. So using inverse norm, if I use inverse norm, I'm going to get the same answer or really close. Rounded to 2 decimals, I think I ended up with 1.439. So use inverse norm just like we did before to, if you have the percent, if you have that percent, you can get the z-score. Just remember that difference, that 0.15, you have to divide it in half. This right here is my alpha. So alpha divided by 2. So we do 0.15 divided by 2. Oops, that's not a 2. That's a weird infinity. So divided by 2. All right, let's move on. Okay, I want you to do this example yourself. This is the same thing we just did with the death penalty. So try this problem, find your confidence interval. So the Gallup organization conducted a poll in which a simple random sample of 1,016 Americans 18 and older were asked, do you consider the amount of federal income tax you have to pay as fair? Of the 1,016 adult Americans surveyed, 558 said yes. Obtain a 95% confidence interval for the proportion of adult Americans who believe the amount of federal income tax they pay is fair. So go ahead and pause this video. If you need to, take a look at your PowerPoint, go back a couple slides and see how I calculated it if you need to. Otherwise, just look at your notes, see if you can find your confidence interval, and then unpause and we'll do it together. All right. So the first thing you need to do is you need to find your p-hat. So my p-hat, I will do that's not the right thing. I will do 558. So p-hat equals 558 divided by 1016. So that p-hat then is 0.55. So I'm going to use that p-hat in my calculations. So remember, in order to do the margin of error, I'm going to do p-hat plus or minus. You guys remember plus or minus from your earlier math classes? This means I add that amount and I subtract that amount. So I need 95% confidence interval. So looking at my z-table on the chart at the bottom, I got 1.96. So it's 1.96 times the square root of 0.55 times 1 minus 0.55, which, newsflash, is 0.45, divided by 1016. So this right here, my p-hat was 0.55. So 0.55 plus all of this, 1.96 square root of 0.55, 0.45 over 1016, I got 0.58. So this right here, all of this equals 0.03. So then that means 0.55 minus 1.96 for 0.55 times 0.45 over 1016 equals 0.53. So essentially, since all of that is 0.03. My margin of error is plus or minus 3%. So I added and subtracted 3%. So the way that we interpret this, my answer is we're 95% confident that the proportion of Americans 18 or older who consider the amount of federal income tax they pay as fair is between 53.53 and 0.58, or you could say 53 and 58%. So whatever the actual, so we can say with 95% confident that all of the Americans 18 or older, if we could ask every single one of them that the actual parameter, that the actual number that think that the amount of federal income taxes they pay is fair is going to be between 53 and 58%. We can be 95% confident that that is true. All right, let's move on. Let's talk, I'm going to show you how to do this in your calculator. So in your calculator, we're going to use stats test 1 prop z interval. So in your calculator, you'll hit the stat button. So you're going to hit this stat button right here, and then you're going to arrow over, use your arrow to arrow over to tests, and then scroll down to right here, 1 minus prop z interval. Make sure that is the one that you're using, because up higher you see you have z interval, you have prop z test. There's a lot of other stuff that has z's in it. You want 1 minus prop z interval. That's what you're looking for. Once you click on that, you're going to put the number of successes you have, which is 558, and then the total number of people polled, which is 1016, and the confidence level, so 0.95. We're not doing the divided by 2 here or anything. Just do 0.95 with your confidence interval. Let me tell you that there were a lot of people in final projects last year that used the confidence interval in their final projects. So this is something to think about, using a confidence interval and margin of error in here. Okay. So put the confidence interval, your X and your N. And when I hit enter on that, this right here is my confidence interval. That doesn't show up very good. I'm going to erase that. So this number here at the top, that right there is my confidence interval. The low number is 0.51862. The high number is 0.57981. So we rounded, but that's basically, actually, I don't like that didn't end up with the exact same answer we had. Oh, it's because the reason the answer is a little bit different is because right here, the p hat is, their p hat is this big, long, not rounded number. We rounded our p hat, and then we rounded our confidence. We rounded when we were working with our margin of error. Because we had to round a couple of times, my numbers are slightly off. That's what happens when you round. The more you round, the further your answers are going to be off. So basically this one is 52 to 58. And so it will probably tell you to use the calculator. If you think your answer is correct and it comes out weird on My Open Math, if they say it's not correct and you're absolutely sure you are correct, send me a message. Many of you have already done this and I've fixed them for you. So it really depends on where you round. Because I rounded early, I rounded a couple times, it ends up slightly off. But this right here is your interval right there. Okay, moving on. Maybe moving on if it lets me. Okay, so margin of error, once again, I've got to fix this lovely thing here. I don't know why things decide not to show up. So margin of error, in order to determine our margin of error, we already did this, but this piece right here is what we're adding and subtracting to our mean, or to our point estimate. We're adding and subtracting that for the margin of error. But in order to find our margin of error, we have to know how many people we are polling. We have to know that. But what if we know the margin of error we're looking for, and we want to know how many people do I have to poll in order to get the margin of error I'm looking for? That is where this comes in right here. Once again, it doesn't show up on my iPad very well. Okay, let me Z alpha. There we go. So this right here, that's really ugly. Let me redo this. Sorry about that. So equals minus, and then this right here is parentheses alpha. Okay. So in order to calculate the margin of error, so let's say that I know that I want a 3% margin of error. I need to know how many people, what sample size do I need? How many people do I need to poll in order to get that margin of error? So this is the calculation you would use for that. However, this formula uses p hat. Didn't we use n right here to calculate p hat? But that's what we're trying to determine. We're trying to figure out what the n is. So without the n, we can't calculate the p hat. So we've had to do a little bit of a workaround in order to do that. So make sure you've written this. Make sure you've written this formula down, and let's take a look at where we're going to go, how we're going to figure out what that p hat is in order to find n. Okay, so these are two possible solutions to our problem. One of them is to use an estimate of p hat based on a pilot study or an earlier study. So let's say somebody else did a study like this. Maybe they did it years earlier, or somebody else did a study and you just want to do your own study. So you can use a pilot study or an earlier study and use their p hat, or you can use this right here. And this is, you can just call p hat 0.5, and it's going to give you the largest possible value of n for the given confidence level and margin of error. However, it's not quite as accurate. You're going to have a lot larger sample size if you do it this way. Your sample size is going to be a lot bigger. We're going to do 2 of them later that's going to use that. So these are our 2 possible solutions. So let's do one of those problems right now. Wait, hold on here. Once again, equals p minus. I don't know why the parentheses disappeared. That's so rude. Okay, so one thing that is really important here is you need to round up to the next integer. So let's say that when I did this, I ended up with, let's just say that I ended up with an answer like 7.3. That this is how many, this is my n equals 7.3. I can't poll 7.3 people. I can't ask 7.3 people questions. Asking 7 wouldn't be enough because I have to have at least 7.3 to get my margin of error. So I would have to ask one more. So we always round up to the next integer. We always do that. We're always going to round up to the next integer. And p hat is our prior estimate of p. So let's take a look at this. Okay. Sorry about my problems here with my computer or my iPad not showing this. I wish I could figure out how to fix that. Okay, so this is if a prior estimate is not available, we use p hat equals 0.5. So this right here is 0.5 times 0 times 1 minus 0.5, because 1 minus 0.5 is also 0.5. So 0.5 times 0.5 is 0.25. That's why we're using that. We're using 0.25 there. So once again, if a prior estimate of p is not available, we're going to use 0.5, and we're going to use the same formula. I'm going to make this a little bit prettier, hopefully. We're going to use the same formula, but we're just going to put 0.25 here instead of a prior estimate because we don't have a prior estimate. So if you're using this type of math on your final project, If you can't find another study doing the same thing as you, just use 0.25. All right. So here is our example problem. A sociologist wants to determine the percentage of residents of America that only speak English at home. What sample size should be obtained if she wishes her estimate to be within 3 percentage points of 90, with a 90% confidence, assuming she's going to use the 2000 estimate obtained from the Census 2000 Supplementary Survey of 82.4. So this 82.4, that's going to be the P that we are using for our calculations, because this is a prior study. So she's going to use the prior study from 2000, but she wants to find today's numbers, and she wants to know how many people do I need to ask today if in 2000 this was the estimate. So let's take a look. Okay, once again, we've got problems. So this, my margin of error is 0.03 because it said 3 percentage points away. So my margin of error is 0.3. I got to quit just circling everything. And so we are using a 90% confidence interval. So remember, the area in the tail is 5%. So since the area in the tail is 5%, we're going to use the z-score for 0.95, or our critical value. So look, in the critical value at 90%, our tail is 0.05. So we're going to use 1.645 from our critical value. So we are using our p-hat of 0.824 because we're using the 0.824 because that was the prior study. That was the prior study. All right. So here's the math. This right here. Okay, so I did 0.824 times 1 minus 0.824. We did 1.645 divided by 0.03. We squared that, and we got 436.04. I can't pull 436.04 people. 436 is too few because it has to be at least 436.04. So we're going to round the value to 437. So the sociologist must survey 437 randomly selected American residents in order to get the margin of error of plus or minus 3%. So she wants that plus or minus 3%. She has to poll at least 437 Americans. Okay. I want you to try this one. We're at the end. This is, you're doing the same thing that we just did. So an economist wants to know if the proportion of U.S. population who commutes to work via carpooling is on the rise. We want to know what size sample should be obtained if the economist wants an estimate within 2 percentage points of the true proportion. 2 percentage points, so 0.02 of the true proportion. We want a 90% confidence interval. If the economist uses the 2009 estimate of 0.10 or 10% from American Community Survey. So I want you to do two calculations. I want you to use the prior survey of 10%, so use the p-hat of 0.1, and then I want you to calculate if the economist did not use a prior estimate. So that would be a 0.5 p-hat. So do the math on both of those and pause this and then come back and we'll do it together. All right, so I hope you paused this. I hope you did this yourself. I'm going to go to a blank screen because I need a little bit more room. So I'm going to go to this blank screen. So first, we want a margin of error. Margin of error equals 0.02. That's the margin of error that I'm looking for. My confidence interval is 90%. So my critical value is going to be 1.645. That's my critical value. My p-hat is going to be 0.10. All right, so do some math here. So n is going to equal 0.10 times 1 minus 0.10. Actually, I'm going to put 0.9 in here because you don't have to actually put in your calculator 1 minus 0.10. Just do that math. Then here, 1.645 divided by 0.02 squared. Put all of this in my calculator and I got 608.86. So I need a sample size of 609 people. In order to get that confidence level, or in order to get that margin of error, I need 609 people sample size. I'm going to do the other one. So I'm going to use, still margin of error is 0.02. Still, this is still the same right here. But my p-hat is different. My p-hat is now going to be 0.5. That is now my p-hat because we're not using a prior estimate. So my n would equal 0.25. 1.645 divided by 0.02, square that, and I'm going to end up with a really large number. So I would need sample size of 1,600. It's not going to fit there. Hold on here. 1,692. See, the benefit of choosing, looking at a prior estimate first, of using a prior estimate, is you'd have to find a lot fewer people to sample. So if you have questions on this, make sure you send me an email or a message and I'll be happy to try to walk you through it more. Make sure you look at your textbook. It does pretty good of digging a little bit deeper into this. And good luck with the homework, and I will talk to you later. Bye.